Thanks. I'll begin with a word of prayer. So, Dearly Father, we thank you for another day just to study your creation, to study abstract algebra. Lord, we thank you for all your many blessings to us this day, Lord. I just pray that you'd be glorified in what we do here. In my prayer, Lord Jesus. Amen. Okay, so just a few little comments. First of all, good if you're studying your homework. Very good, very good. We don't have time to talk about homework in here because we have a few precious lecture hours, and I have 10 office hours a week. You can come talk to me about homework anytime during those. That's what they're for. So make use of them. Just that's one comment. Of course, you can also send me emails. I do try to respond to emails. Lorenzo, do I usually respond to email?
Depends on if you like the email or not.
Ah, good answer. I usually do. I try to. Now I'm getting distracted. Let's see here. It's not the answer I was expecting. So let's see here. So it's good that if you're working on the homework, you should be working on the homework. You should be reading Galilean. You should be able to tell from the lecture notes and also the course planner what parts of Galilean you should be reading. You should also have noticed that I have not said a word about the dihedral group, right? Or symmetries just yet. That's because Friday I'm talking about symmetries in here, okay? Today I'm going to add a few more groups to the list. The big event for today is I'm going to start talking about modular arithmetic, okay? Modular arithmetic and subgroups. Now, I'm not going to do modular arithmetic carefully today. I'm just going to make all kinds of greedy claims about it. All right? Try to describe to you how it works. How many of you have studied modular arithmetic before? Who has never seen like Z mod n in any class? Wait a minute, I don't have to develop it. We can just go on. Yes. Now, I will come back to it next Monday and Tuesday because I think you need to see it again. All right, but for now, here's the definition, basically. Mostly this is just a subtle notation. We'll say Z sub n is equal to 0, 1, n minus 1. All right? And we're going to define addition and multiplication here as follows. If A and B are in Zn, all right, then A plus B is equal to C, and A times B is equal to D, all right, where A plus B minus C and A times B minus D are an element of the integer multiples of n, nz as it's known. Now this nz, what's this notation for? That just means the set of n times k such that what? K is a integer, right? So it's like 0 plus or minus n plus or minus 2n plus or minus 3n plus or minus 4n. Well, you get the idea. All right. So just to give you an example of this, here's the addition table, and here's the multiplication table for Z3. I'll tell you what I'll do. No, yeah, fine, Z3. So we got 0, 1, and 2, that's Z3. So here, and then in the table, you write what you get, right? So, what do we got? Wait a minute, a bad marker. What am I doing? My markers, yeah, they are. So, excuse me. Of course, if you add 0, get the same thing back again, right? 1 plus 1, 2. 1 plus 2 is what? Well, 3, but in Z3, that's 0. All right? Well, that's interesting. 1 plus 2, 3, which is 0. 2 plus 2 is 4, but 4 is 1. Yeah. So there is the addition table in Z3. All right. In fact, Z3 forms a abelian group under addition with additive identity 0. Multiplication. Well, 0 times anything is 0, right? So the first row and column are easy. And, of course, we've got 1, 2, 2. The interesting one is 2 times 2, which is what? 4, which is 1. Yeah. So pretty clearly, if you take Z3 and you pair it with multiplication, not a group, right? 0 has no multiplicative inverse, right? That's kind of a problem. Now, on the other hand, though, if I look at Z3, right, and I focus my attention in on like a subset of it, right? What if I just look at 1 and 2, like this piece right here, right? And I say G is equal to the set containing 1 and 2 with multiplication done mod 3, right? I can define that as a multiplicative group, right? It's a group with 2 elements. It is a group, right? What's the inverse of 2? It's its own inverse, right? 2 inverse is equal to 2 in this group. All right, so apparently the Zn is not generally, right, a group with respect to multiplication, but we might be able to take some subset of it and make it a group with respect to multiplication, right? Zn with respect to addition is going to be an abelian group. So together, you put both of these things together, what is Zn? Well, Zn is what's called a ring. There's an addition and a multiplication, right? And they behave together nicely. And so Zn is a nice example of a commutative ring with identity, as I talked about in lecture 1. The thing I just boxed in red is actually an example of a field, right? Well, I'm sorry, Z3 is a field, actually, right? What's a field? A field is a commutative ring where every non-zero element has a multiplicative, I can't spell, inverse, right? So, for example, Z3 is a field. All right. That's mostly important because we use fields to build group examples at the moment. We're not studying fields for their own sake just yet. All right. So, the multiplicative group I just established in this exhibit in this example is part of a larger story, right? You guys probably recall from another course you took that if the greatest common divisor of integer n and an integer k is equal to 1, then there exists some k such that what? Such that, oh, I'm sorry. I meant to say, oh yeah, I'm sorry, j here. There exists a j such that what? Such that j times k is equal to what? 1, right? Excuse me. And I'm talking, of course, modulo n. I mean, there's more to it if we're just working with integers, but we'll get to that lectures 4 and 5, okay? But the point is, in Zn, there's a multiplicative inverse, right? If the greatest common divisor of k and n is 1. So there's a definition. This is one of those things we'll keep working with in here. Un, all right, is a subset of Zn, all right? And we define Un to be what? It's equal to, it's k in Zn, such that what? Such that the greatest common divisor of k and n is equal to 1. This is supposed to be a capital U. I don't know if you can make it out or not. This is the so-called group of units. Group of units in Zn. So you guys can tell me, G, this G back here, what was it actually in terms of this notation I just unveiled? Or you already know if you've been reading Galilean, right? This is what? This is equal to U3, right? Okay, so the group of units is a multiplicative group, and the multiplication is done mod n. Let's see here. Let's look at an example. Let's see here. Let's figure out what would U10 be. My current notes have a 4 in them, which is nonsense. But none of you have printed that out yet since I posted it like 3 minutes ago. So no damage is done. Sorry, I'll fix it soon. U10, what should that be? That should be all numbers relatively prime up till 10, right? So you guys help me out. What is that? 1? I think I did the easy part. 2 is out, right? 2 and 10 have a common divisor of 2. 3 is good. 4 has got a common divisor of 2 with 10. That's out. 5, 2 times 5 is 10. That's not good. 6, 6 has got the 2 again. I guess you guys are like, get the 7 already. All right, 7, fine. 9, yeah, there you have it. So if I was to draw, by the way, I should tell you, it seems like I have some kind of animus against him. I haven't mentioned his name much yet. Cayley. This is an example of a Cayley table for the abelian group Z3, right? So if I was to draw the Cayley table for Z10, it would be 10 by 10. It would have 100 things, the additive group Z10, right? So this is a quaint little 4-element multiplicative group that's sitting inside that in some sense. They're governed by the same rules of arithmetic, right? But they are completely separate groups, right? The additive versus the multiplicative. I'm taking a second to say these things for you guys because my personal trouble in group theory was mostly revolving around my inability to remember that multiplication and addition are different things. Okay, so I know it seems like a small thing, but it's actually kind of a big thing. All right, so multiplication here, how's it go? We can fill out this Cayley table, 16 elements, we got time for it. I'll do the easy part. First of all, you know, if I ask you to do one of these tables on the test, if I have any decency, I'll say, give me a reduced Cayley table. And reduced will be writing everything that I haven't written yet. Multiplication by 1, okay? Right? As long as you put the identity first in the table, the first row and column are pretty much for free, right? Now we have to think. 3 times 3 is 9. 9 mod 10, 9. 7 times 3, 21. 21 mod 10, 1. 3 times 9, 27. 27 mod 10, 7. Let's see here. 7 times 7 is 49. 49 mod 10 is 9. And then 9 times 7, 63, 3. 9 times 9, 81, which is 1. All right. If you know you're working in a commutative context, it means that the rest of the table is given to you for free, or you can multiply them separately to check yourself, right? Because A times B is B times A in this context. So of course, this is 1, this is 7, this is 3, you know? And while we're at it, you can see some kind of cool stuff here, right? Like, for example, 3 times 7 is equal to 1, so therefore 3 inverse is equal to 7, right? Perhaps this is more shocking if I write it like this. 1/3 is equal to 7. But that's what arithmetic mod 10 works like, right? 3 inverse is playing the role of 1/3 in our previous calculational experience. But anyway, we don't write this. Strike this from the record, all right? I do want you to write 3 inverse, all right? We've defined this. We have defined this. We have not defined that. In fact, well, anyway, all right. Can you tell me anything else from this? How about 9 times 9 is what? Is 1, right? So we have this kind of cool thing. 9 times 9 is 1. Yeah, 9 is its own inverse, just like, just like 2 over here. But the rules for 9 and 2 and 3 and 4, they're totally different if you work with different modular systems, right? Like mod 3 and mod 10 are different worlds. All right. How about Z11? Let's look at another example here. How about U11 in Z11? Which numbers are relatively prime to 11? Smaller than 11, relatively prime to 11. Which are what? All of them, right? Yeah, exactly. So this one's easier. It's basically just, okay, so U11 is just equal to 1, 2, 10, okay. Let's see here. If I can come up with kind of a cute example. 4 times 5, right, is equal to 45. What's 45 mod 11? Yeah, it's 1, right? So therefore, 4 inverse is equal to 5 in this context, right? All right. Oh, I'm thinking of, did I say 4 times? Oh, I was thinking, I'm sorry, I wasn't done writing. There. Phew, that was close. I meant 9 times 5. Sorry about that. Sometimes my mind skips. Anyway, this is, of course, part of a larger pattern. It's fairly obvious to make this observation, right? If we look at if we look at ZP, right, where P is a prime, this is a field. Why? Because basically ZP is what? It's equal to UP, right, unioned with 0. Everything that's not 0 is relatively prime to P. So Z mod P is everything except for 0, all of which have multiplicative inverses, as I just, well, we haven't proved that, but we will eventually. But that is in fact true, whether or not we've proved it. All right. So fields. What fields do we know then? We know rational numbers, real numbers, complex numbers, right? And now Z mod P, where P is a prime. Lots and lots of fields. I would point out that the thing I did last time generalizes. In fact, we can also define G, L, and F to be the set of n by n matrices, right? Such that the determinant of A is not equal to 0. This is just as well defined for n by n matrices over a field as it is for n by n matrices over real numbers. Okay, so there's a whole truckload of groups that we can study there, G, L, and F. I don't have much more to say about them right now, but that's the thing. All right, so that brings us to the study. Now I needed to introduce these things because what we're about to study is kind of boring for the groups that I talked to you about last time. All right, because all of the things I talked to you about last time, pretty much without exception, are infinite groups. Real numbers, complex numbers, rational numbers, they're just endless, right? But these, on the other hand, are finite groups, the ones that are groups, right? And so for finite groups, the notion of order is actually interesting. Well, I don't know. I guess order is also an interesting concept for infinite groups, in the sense that if the order is infinite, it captures that it's an infinite group, you know? So that's a thing, I suppose. So here's the definition. The number of elements in a group G is denoted is the order, and we denote that just like this, right? If the number is not finite, then it's said to be of infinite order, all right? And we still use the symbol. I mean, you can just write this equals to infinity in the case that it's of an infinite order, all right? What's the smallest order a group can have? Could a group be order 0? Why or why not? No, because what? Well, we're thinking about that. How about Zn? What's the order of Zn? N. Very good. If we look at G equals to R, under addition, if you like, right? Now, the smallest the order could be would be 1. Why? What's in every group? Identity, right. So we're stuck with that. Can't have a group of order 0. Now, notation that I should mention, all right. We need this notation to make sense of the next definition. What do we mean by G to the N? I think I've used this maybe last time. I'm not sure where. I feel like I might have, but this is defined to be as follows. So Gn plus 1 is equal to G sub n times G, right? For n in the natural numbers, right? And let's see, to get the recursion starting, we do what? G to the 1 is equal to G, right? So this defines positive integer powers in a multiplicative group, just like that. And how do you extend this to negatives? Like, what is G to the minus n? What would that mean if n is an integer? It's very simple. It's just G inverse to the n for n and n. I guess there's one thing I've left out. What else do I need to say to complete the story here? What do we define G to the 0 to be? Not 1. Yeah, we will say E here, right? It would be 1 if E is equal to 1 in the group we're studying, if that's our notation. Okay, so that's integer powers of a group element. That's how you do it. They're defined recursively. What is the definition? But of course, there's also an additive side of this story, right? Excuse me. If we have 0 times, let me just get to the point here. I'm going to do this a little bit more sketchily, if you don't mind. N times G is equal to G plus plus G times. And how many of these? N some n's. Right? Like that comment over here is basically the same things going on over here, right? G to the n is G times G times G times G n-fold times. But to be careful, I give you these definitions. Conceptually, I think of it like that. It's true. What would, if n is negative, how would you do this if you had minus n? What would that mean? Be minus G, minus G, minus G. You know, I mean, you get the idea. Right? Or you could just be more to the point, minus ng would be equal to minus ng. That would do it. You could define it that way if you wanted. All right, I think I'm saying not terribly interesting things. Let me move on. My point to you is that okay, so this would be for an additive group, that'd be for a multiplicative group, and we should define these things, right? Because you shouldn't assume that powers are defined already for you. There's something we should build from the group multiplication in here, all right? Okay, anyway, with that settled, we can define the order of an element. What's the order of an element? Order of G and G is the smallest end positive integer for which what? G to the n is equal to so we're in a multiplicative group, so g to the n equal to what? Guys are killing me. E. Excuse me. Oh boy. Here we go. All right. Now in the additive world, how's this look? Ng equals to 0, right? So in an additive group, that would be order n. And n minus 1 times g is not 0. Right? If you take g and add it to itself n minus 1 times, it's not 0 if the order of g is n in an additive group, smallest integer. So let's see here, because this is an interesting concept, of course. Let's see if we could think of an example of this. How about Z4? Oh, oh, okay, I'm sorry, I got confused here all of a sudden. Oh. What do we, if no such n exists, also what do we say? Sorry, my mind is skipping again. That's if there exists an n, right? If an element has infinite order, what would that mean? If no such n exists, right? G has infinite order, right? Can you guys tell me something with infinite order? How about the real numbers under multiplication? Take anything in here pretty much except for 1, right? If you look at a to the n, is it equal to 1? Does that have a solution? How would you solve that? So remember that thing I said about Calculus 2 having weird overlaps with this course? Here's one of those. So that's what? N ln of a. I mean, I guess more to the point, this is a to the 0, right? And then you can use the 1-1 property of the exponential function, woo, if you like. And that says n equal to 0, but we've assumed that n has to be a positive integer. Anyway, sorry, let me shut up. The point is, a not equal to 1 is of infinite order, right? There's no way you can take a non-zero real number which is not equal to 1 and take it to some power such that it becomes 1, right? It's either more or less than 1 and it keeps being that if it's positive, and if it's negative it does all kinds of crazy stuff, but it never gets back to 1, right? Oh, but yeah. Sorry, this is not positive real numbers, right? This is non-zero real numbers. Okay. Okay, next example. How about this? Just to try to expose you to this idea. How about a Z4? That's 0, 1, 2, and 3, right? So let's just study what's 1 plus 1 plus 1 plus 1 is equal to 0, right? 3 plus 3 plus 3 plus 3 is equal to 0, right? But what? 1 plus 1 plus 1 is equal to 3, which is not equal to 0. And 3 plus 3 plus 3 is equal to what? 9, which is 1, which is again not equal to 0, right? And of course you can also, you can verify that 4 is the smallest positive integer for which 1 added to itself that many times gets you back to 0, right? And the same for 3. In contrast, 2 plus 2 is what? 0 mod 4, right? So you can see from this clearly that the order, oh, I'm sorry. Yeah, the order, there's a notation. Also, what's the notation for the order of G? Sorry guys, I'm fighting the urge to cough more and more as I go on here. There's a simple notation, right? So the order of the element G is just equal to n. That could be infinity, right? So for these guys, the order of 1 is the order of 3, which is 4, and the order of 2 happens to be 2. Okay? So this is the notion of order of an element. What class? Are they getting out now? Like, that's nuts. Funny. We've still got like an hour left, right? What's that?
So would the order of 0 be 0, or is that question answered?
The order of 0 seems to me is, I think it's 1. It's either 1 or it's undefined. That was one of the things I was trying to cipher from Galen today. I was just putting notes together, and I couldn't quite see it. He also dodges it in his example. So I don't want to commit to that just yet. It's a good question. A very good question. Okay, so definition. If H is a subset of a group G, all right, and H is a group with respect to the operation of G, then H is a subgroup of G. You guys this might be kind of reminiscent. Remember we studied subspaces in linear algebra? It's much the same idea, right? A couple special things here, kind of silly examples. First of all, G, okay, so also notation for this is what? We write H subgroup of G. That is not read less than or equal to. H less than or equal to G equals you don't know what you're doing. Okay, but no, this is read subgroup of G. Now, it would make sense, and in fact it is true, that the order of H is less than or equal to the order of G. That you could prove. I'm not going to today, but it's true. At least when they're finite, that's meaningful. Anyway, so there would be less than or equal to. Those are numbers, that's groups. Okay, so G is a subgroup of G. That's kind of a stupid example. So if you don't want to allow this, all right, if you want H a subgroup of G and H not equal to G, what you can write is that H is a proper subgroup of G. All right? That's the first silly example. The second silly example is the case H is just equal to the set containing the identity in the group. This is also a subgroup, almost trivially so. I mean, well, trivially so. And so if you want to say that, if you have a subgroup, all right, and you want it to be non-trivial, that's what you say. You say, I want a non-trivial subgroup. Saying a non-trivial subgroup means your subgroup is not just equal to the set containing the identity. By the way, just a comment. This is not equal to E. Why? E is an element. The set containing E is a set. These are not the same things. Okay. Question for you. Is Zn a subgroup of Z? Well, both of those are groups. We've already given them operations. Then what? Then no. No is correct. Why? Because it's this, exactly. This has modular arithmetic, right? And this just has arithmetic, right? They have different operations. Even though it appears, of course, that Zn is just a subset of Z, they have different operations, so Zn cannot be a subgroup of Z. The connection between Zn and Z is a little bit more subtle than just subgroup. Okay. Another question. You had a homework, right? You're working on it currently, some of you. You know what I'm talking about? The one with the 2x2 matrices? Let's see here. You got G, A, such that A is non-zero, right? Real number? So you're asking your homework problem to show that that's a group. Is this a subgroup of GL2R? They do seem to have the same operation, don't they? They're both defined by matrix multiplication. And yet you know something's amiss because you know the determinant of AAAA is 0. So what does that say about your G as it relates to GL2R? It's not even a subset, right? So it can't be a subgroup. It only appears to be a subgroup of 2x2 invertible matrices. Well, it's not it's clearly not invertible. It's worse than that. If you look at what the identity element is in your group, you'll find out it's not the identity matrix. The only thing that really unites GL2R and that homework problem are the fact that they both use 2x2 matrices. But that's about it. Okay? So don't be bothered by that. Embrace it. Reap the whirlwind. I'm sorry. Wait a minute. It really seems kind of inappropriate. All right, where were we? As usual, behind. All right, so not really. We're not behind. Okay, so what are the fundamental theorems about subspaces? Excuse me, subgroups. My linear algebra was showing just there. Sorry about that. I'll try to put it away. So we have two theorems. Right? Theorem. So this is the one-step subgroup test. Right? It says if H is a subgroup of G and H is non-empty, those preconditions are important. Then H is a subgroup of G if whenever, excuse me, my mind skipped again, if A, B inverse is an element of H whenever A and B are elements of H. Let me rewrite that sentence a little bit more directly, let's say. So what it's saying is that if you can show, if you let A and B be elements of H, you should be able to show that that implies that A, B inverse is an element of H. This is what you have to show. you have to demonstrate to apply the one-step subgroup test. Yes, sir?
Is it A B inverse or AB inverse?
It's A, B inverse. What do you mean? I would write parentheses.
Okay, I'm just
I mean, you have to write parentheses. If you try to write A, B inverse without parentheses in here, I kill you. So, but I hear what you're saying. Yeah. I mean, if you're going to be are you planning to be a high school math teacher? Oh, okay, well, it's less relevant to you. But I mean, my experience is that students are so very stingy with parentheses. You'd think they cost a lot or something. I mean, and what's up with fraction symbols? Like, is it so hard to draw the whole fraction symbol? Like, A plus B over C. It's like, what? What am I supposed to do with that? But it's just, that's why I get paid the big bucks. All right, so the two-step subgroup test. Two-step subgroup test says basically almost the same thing. It says if H is a subgroup of G and H is non-empty, then not H is a subgroup, H is a subset. These are subsets, obviously, otherwise it's totally circular, right, folks? If then H is a subgroup of G, H is subgroup G if whenever, if A, B, let me just enumerate them. If 1, AB is an element of H whenever A and B are in H, and 2, if A inverse is an element of H whenever A is an element of H. I don't usually use this whenever language, but I'm trying to just follow Galilean at the moment. I prefer what I wrote in green here. I mean, operationally, that's what you have to do here, right? You have to assume A and B are in H, show that the product AB is in H. Assume A is in H, show that the inverse is in H in order to apply these tests, all right? Now, I'm not going to go through the proof of this in class. The proof is in the notes. You should read it. All basically it is checking that the condition up there gives you closure, identity, inverse, and associativity. Associativity almost comes for free. Very simple proof. And the proof of this is even easier. I can go through the proof of the two-step subgroup test. It follows immediately from the one-step subgroup test. Suppose you have a non-empty subgroup, and suppose you have these two conditions, all right? What I want to do is show that suppose you have a non-empty subset H that satisfies these two conditions, right? Notice then, what that means is if I pick A and B in H, then by 2, B inverse is in H, right? So, proof of two-step. But then what? Then you have I'm lost myself here. I'm trying to show that A, B inverse is in H again, right? But check it out. So by 1, we know that A, B inverse is in H, right? Because I have that B inverse is in H, and I have A is in H, so I have an A and a B in H, so I get that the product of A, B inverse is in H. So what have I just shown? I've shown that if A and B are in H, then A, B inverse is in H, hence by the one-step subgroup test, H is a subgroup. If you didn't follow what I said just now, it's not really that big a deal. If you read Galilean or my notes and think through it carefully, you'll get it. Don't stress yourself on this. You really can, everybody can understand this. It's not that big a deal. What I should show you is applications. Excuse me. Maybe you should order a new instructor. Let's see here. Gracious. Yes, a more attractive one. Yes, thank you for bringing that up again. Thanks a lot. Yeah, sure.
So you said that's the proof of the two-step?
Yep.
Okay.
The one step is proved in the notes.
Okay.
It's lengthier, but it's pretty straightforward. Yeah. So let's see here. An example. Did you have other questions or? Oh. Okay. How about this? If we look at H equal to what's called SL, and I'll look at the real one just to keep it more familiar. This is, by definition, n by n matrices such that the determinant of A is equal to 1. I argue that this is a subgroup of GLN. All right? All right, so point number one, I would point out that the identity matrix, right? The determinant of the identity matrix is equal to 1, right? So therefore, 1, the identity rather, is an element of H, which is thus not empty. So it's definitely not empty. Also, it's also clear that H is a subset of GL and R. Why? Because the determinant of A equals to 1 is not equal to 0, right? And we defined GL and R last class to be the set of matrices with non-zero determinant. Certainly if the determinant's 1, it's non-zero. So it's a subset. So we have a non-empty subset. So now what do you guys want to do? Do you want to try to use the one-step or the two-step? Two-step, all right, yeah. So we'll start with A and B in H, right? Then what does that tell us? That tells us the determinant of A is equal to the determinant of B, which is what? 1. Consider the determinant of A times B, right? Is what? Yeah, property determinants, determinant of A, determinant of B, which is what? 1 times 1, otherwise known as 1. Why did I do this? Because that shows what? That shows that the product of A times B is again in H. So therefore, this H is closed under matrix multiplication. Now we're using the two-step subgroup test, right? So we have one thing left to do. We need to show it's closed under inversion, right? So, again, let A be an element of H where, so the determinant of A is equal to 1, right? So therefore A inverse exists with what? It exists in GLNR if we're not going to assume the point, right? This we know from linear algebra. And so there exists an A inverse in GLNR with A inverse times A equals to what? What makes it the inverse is when you multiply them together, you get the identity, right? So then what? Basically the same thing we did in step 2, right? Take the determinant of both sides, what do you get? The determinant of the identity is 1, right? So what's this say? If the determinant of A is 1, then what does this have to be? Right. You could do more algebra, but this implies, of course, that the determinant of A inverse is equal to 1. Therefore, A inverse is an element of H. Thus, H is a subgroup of GL and R by two-step subgroup test. Now he has a nice example, I think it's example 4 in Galilean, where he defines a subgroup to be like the set of things in an abelian group which square to the identity. That's a very nice little example. I don't think we have time to do it in class here, but I would urge you to read it because it's very, very simple to understand and a nice showcase of this. So next time, I'll still be in lecture 2, technically, but I'll hopefully have lecture 3 posted. So it'll probably take me another 10, 15 minutes to finish up talking about centralizers in the center, and then hopefully we'll spend about the last 30 minutes talking about dihedral groups and that business. All right, thanks guys.